Please send your homework leftward. The reason we covered functions is to examine a sequence in that sort of a light. So a sequence is an ordered set. But in that fashion, we can think of that ordering as assigning an element of the set to every number. So if I had a set of things, I could say this is the first element, the second element, a function from the set n, the natural numbers, to s. Remember, that's 0, 1, 2, 3, dot, 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 to s. So I would have the thing in s that goes with 0, the thing in s that goes with 1, the thing that goes with 2 and 3. These are the elements of s. And those are the terms in my sequence. Here is a case where using 0 in the natural numbers, we said we wanted to do that back earlier in chapter 2, but now most often we don't use S0. We start at S1. And if my elements are not from any particular set, we might just call the set arbitrarily, instead of S, call it A. So you'll often see this expressed as A1, A2, A3. And then the ith term until we get to the last element in our set, whatever that is. This list might go on, since n goes on forever. This could go on to infinity, right? So I could write a function like this and say that f of I is 1 over I. And if I do that, then my sequence should start with 1 over 1, then 1 over 2, 1 over 3, 1 over 4, and so on, right? A set meant I didn't care about the order. I want to emphasize that I do care about the order. I shouldn't use a set brace. Instead, we're going to use a set of parentheses. Why? I use a set of parentheses. Oh, like an ordered pair. X, Y, right? The parentheses indicated that that had an order to it. Same deal here. My parentheses indicate an order to my items. Questions? It seems pretty straightforward, right? Here's a list in order of my things. I don't have to describe them with a formula. What does it mean for a number to be prime? A term we will come back to in chapter 4.
It can't be like it's only divisible by 1 in itself.
It's only divisible by 1 in itself. So the first prime number is 2. Only thing, whole numbers that divide 2 are 1 and 2. So 2, 3, 5, 7, 11, 13, and so on. I don't know of a formula for this function. By the way, if you could find one, you would break every single encryption algorithm on the face of the planet instantly. That's $1 billion question. Because you'd make computer hacking impossible to beat. Often, giving a description of my sequence is more valuable than actually coming up with a formula for it. An arithmetic progression or an arithmetic sequence is where every 2 terms have a common difference. So if you subtract 2 numbers, one right after the other, you'll get the same thing every time. Seth, give me a number. 20. Kari, give me another number. 33. Okay, so I could say we're going to start at 20 and we're going to go up by 33 every time. From here to here, I added 33. From here to here, I added 33. Right? What's the next number? Say again? 50. I'm adding 30. I'm adding 33 again. What's the next number? Sorry. Not give me another number, but that helps. 152. As a matter of fact, I could come up with a formula for this, right? I could say that each number here is a mark on a line. If I wrote it like that, then I would be saying that every time you go over 1, you go up 33. That's the definition of slope. So this could look like a y-intercept of 20 and a slope of 33. Notice to do that, I had to start with f of 0, not f of 1. Okay, I can do it either way. Arithmetic progressions show up in hundreds of different applications. As a matter of fact, we make the assumption that a lot of the behavior we see is truly a straight line behavior. That's why we do things like lines of best fit and linear regression in statistics. Oh, I think this is a straight line idea. So let's change the word arithmetic to geometric. And then instead of adding the same term, we'll multiply. So I'll run with 50 this time. If I start with 50, let me pick a small number for a ratio. What did I do to get from each term to the next one? I divided by 2, or I multiplied by a half. Since I'm thinking of this as a ratio multiplication, I'm going to think of it as multiplying by a half. And again, I could come up with a formula for this. That formula is not a straight line this time, right? But I have seen this graph before. Something where as I go forward, I multiply by a half every time. That actually looks like a graph I've seen before. I know this shape. I used this shape in Calc 1. What is this shape? Maybe it would be easier to understand if I drew it like this, going the other way. That's exponential. The fact that it's going like this means it's exponential, where the base is smaller than 1. Oh, like 1/2 is smaller than 1. As a matter of fact, I didn't multiply by any 1/2 to get 50, did I? So f of 0, sorry, that's leave that as n up there. F of 0 is 50, because 1/2 to the 0 is 1. F of 1 is 1/2 of 50. But I multiplied by a half and then a half again, 1/2 squared for f of 2. Well, that's a quarter of 50. That's 12.5. Again, geometric sequences show up all over the place. An interesting point. Back in the 1870s, 1850s, a guy by the name, started to say Verhulst, and that's wrong. Malthus. Malthus said, population is a geometric behavior. Population grows like that. And it's got a big growth factor, so we keep growing. People, there are more and more and more and more and more people, faster and faster. But agriculture is arithmetic. And in the 1850s, Malthus predicted that no matter how fast we did our food growth, no line could ever keep up with this sort of a growth. And Malthus predicted that by the year 1900, the city of London would be so densely populated that no two people could have more than a square meter apart from each other. Population density of London would be so tight that nobody could move. Clearly, he was wrong. What happened to change this was a huge change in agriculture. All of a sudden, huge mechanized farming, the Industrial Revolution, applied to agriculture, gave us newer ways of growing even more and more stuff. We saw this again in the 1970s. A guy by the name of Paul Ehrlich, I'm not sure about this Paul, wrote a book called The Population Bomb. And Ehrlich was convinced that we were going to overpopulate the planet and cause massive famines. He was right. Ethiopia and a large portion of sub-Saharan Africa went through huge famines in the 70s and 80s. But then again, we changed the way we were going to do farming, and all of a sudden we were able to feed people. We moved them. And population is still outpacing our catch-up efforts. I see this today. Guy who worked at the University of Pennsylvania, Michael Mann, did this exact same sort of claim about global warming, that the method in which the planet is warming is geometric, and all of our warming reduction strategies are arithmetic. This is a problem. It's not a new problem, but it is a problem. Hopefully, we will again come up with some method that allows us to cheat Malthus's idea. Some sequences are defined in terms of other terms, like this one. Here I was told, hey, you multiply the number that came before. You add to the number that came before. This sort of a definition is called a recurrence. So AN, the nth thing in my sequence, is defined by the numbers that came before it. Our geometric sequence can be defined this way. We started with 50 because that's the number Quentin gave me. And then I multiplied by a half each time, right? I took each number and I said that is half the number that came before it. My arithmetic sequence start with 20 and add 33. So A1 is 33 more than A0. A2 is 33 more than A1. And this allows you to write this, hey, go back and look at what just came and do something to that number. There is no required limit to how far back I look. So here's an interesting sequence. Start with the numbers 1 and 1. That's F0 and F1. Then to get F2, you add those two numbers. F2 is F1 plus F0. F3 is F2 plus F1. Each number is the sum of the two numbers that came before it. Write out for me the first 5 or 6 numbers we're going to get in this list. What's next? Heard somebody mumble. The next number comes from adding the 2 in front of it. The next number comes from adding the 2 in front of it. The next number comes from adding the 2 in front of it. This is also a recurrence relation, but it's a recurrence of depth 2. I have to go back 2 numbers. These were recurrences of depth 1. This particular sequence comes from a book written by a gentleman, Leonardo of Pisa, son of Boccaccio. The book was called Liber Abaci. The book of counting, Abaci, abacus. This is one of the first books to use the numbers that we use today, the Hindu-Arabic numeral system, in whenever the hell this was written, 1500s, 1600s. But we know Leonardo more by his last name, because in Italian, you use son of as fib. Fibonacci. Fibonacci. This is called the Fibonacci sequence. In Liber Abaci, it's about a bunch of rabbits. You have one rabbit. At 1 month old, that rabbit can breed. So if you start with one pair of rabbits, at the end of 1 month, you have one pair of rabbits. Those rabbits start to get together. It takes 1 month to have a healthy child. At the end of 2nd month, you have your pregnant rabbit gives birth. You end up with 2. But you have one breeding pair and one young pair. It takes a month to grow up, but the breeding pair starts all over again. You know, they breed like rabbits. And so all of a sudden, at the end of that month, they give birth again. You end up with 3. But now you have 2 breeding pairs, because the breeding pair that was young in month 2 is now old enough. On and on it goes. All Fibonacci wanted us to do was to learn this sort of addition pattern and practice using the numerals. Questions? Please note, with our previous 2 recurrence formulas, the geometric one and the arithmetic one, we were able to write a formula. It would be really nice to know if there's some formula for this. Finding that formula is called finding a closed form for our recurrence. It's also called solving the recurrence relation. Now, in this case, finding that formula is really freaking complicated. So I'm not going to do it. I am going to tell you that there is such a formula, and we'll figure it out in chapter 8. If you're interested, you should look up something called Binet's formula. Which was solved in the 1850s, I believe. But if I have a simpler recurrence relation, I should be able to find this closed form. An example. This is a recurrence relation. Write out the first, I don't know, 6 of them. The first 6 terms in this sequence. Starts with a 5. What are the next 5 numbers? The next number. A1 is minus A0. 0 is 5, so A1 is minus 5. What's A2? All I do is I put the 2 here. The 2 says, hey, that's minus A2 minus 1. That's A1, right? This is A0. This is A1, A2, A3, A4, A5. A2 is negative A1 minus a minus 5. Positive 5. What's here? And so on, right? Hey, this actually reminds me of another series we already looked at. I'm multiplying by the same number every time, aren't I? What's the number I'm multiplying by every time? Negative 1. So I could think of this as having a formula that says start with a 5, multiply by negative 1. How many times? Here I multiplied by a negative 1 once. Here I multiplied by a negative 1 twice. Once to go from here to here, once to go from here to here. Here I did it 3 times. Oh, I should multiply n negative 1s to get the right sign on my this is a closed form. I now don't have to say, I want to know the 73rd term. To know the 73rd, I need the 72nd, 71st, 70th. Forget about it. I can just plug 72 into here, 73 into here, and I can get one answer. So this expression is a closed form for this particular sequence. Maybe. Y'all are looking at me like I've just decided to whiz on the table or something. Talk to me. Lunch was too good, you're still all checked out. This is still a recurrence, but this time you'll notice there's a term in here that isn't about an, it's about n itself. If I tell you that A0 is 4, A1 requires me to use this formula. What is A1? about A2? It's A1 minus 2, because it's the n that goes there. So that would be 3 minus 2, that's a 1. Let's say 3. Careful. A2 minus that number. That number is going to change every single line, isn't it? A4 is A3 minus 4. Oh boy. Is there a way that I can write a closed form idea here? The answer is maybe, but I think it helps if I look back at these terms and try and make a common behavior out of them. So let's start this process over. We said A0 was 4. A1 was 4 minus 1, which we got to be 3. A2 was 3 minus 2, right? Where the 2 came from the fact that this was n equals 2, and the 3 came from the line before. Yes? But the 3 coming from the line before means I could actually write this as 4 minus 1 minus 2. Isn't that where I got the 3? I got it from the line before. Well, if I do that again, what's A3? It's the line before minus 3. And A4 is the line before minus 4. Hey, wait a second. What's AN? It's all of these numbers, that goes from 1 up to here, right? So start with a 4 and subtract 1, subtract 2, subtract 3. Keep going until you subtract n. Does this work for 5? If that's right, then A5 should be 4 minus 1 minus 2 minus 3 minus 4 minus 5. That's the line before minus that number. Hey, this seems to match up. Is there a nice formula for this? Maybe. If I could figure out how to write this part nicely, then I could come up with a nice formula for this. I don't know it off the top of my head. I promise we'll figure it out sometime in chapter 4. Questions? Going back and finding that closed form is not obvious. So quite frequently what we do is we say, hey, is this geometric? Hey, is this algebraic? Does this look like something I've already seen? Does this look like a known sequence? This process of using the previous number to find the next one, this is an iterative procedure, a recursion. We're doing this forward substitution idea. On page 171, there's a list, another box. that shows me some sequences I should probably try to recognize. Squares, cubes, fourth powers, the Fibonacci sequence, exponentials, doubling, cubing. What was that exclamation point thingy again? Factorial. And that was a recursive behavior, wasn't it? You multiply all the numbers back down to the aha. Here's a sequence of factorials. So when I'm looking at a given sequence, it is to my benefit to say, hey, is it related to one of these? Is it kind of like something I already know? This is very much the same idea we did in proofs. Oh, I've seen an argument like this before. Can I make that argument here? Here's the sequence. That's all I'm given. Here, find a pattern. You've got to be kidding me. Well, to go from here to here, I added 12. But to go from here to here, I added 40-something. Forget it. I'm not doing something arithmetic. Did I multiply by the same thing each time? What's 14 divided by 2? 62 divided by 14 is not 7, is it? Okay. I'm not multiplying by the same thing each time. But if I look at that list we were just looking at, I say, hey, wait a minute. Powers of 4. 4 to the first is 4. What's 4 times 4? 4 times 4 times 4. It'd be 16 times 4, wouldn't it? What's 16 times 4? You have a calculator. You don't have to do this in your head. 64 times 4. 256 times 4. Multiply that by 4. What's the difference between the top line and the bottom line? Get the top line, I take this line and I subtract 2. So I'm going to go ahead and I'm going to say that the formula for this is 4 to the n minus 2. Starting at n equals 1. But I wouldn't have been able to do that without the list inside. Textbook. Powers of 4 is not something I magically keep in my back pocket and happen to have memorized. Hell no. So what happens frequently is I will look at a list of numbers and go, I don't know what the hell this is supposed to be. I don't recognize this obviously. But perhaps there's a formula under there that someone else has already recognized and written down. There's a website, oeis.org. You give it a sequence, and it will tell you patterns that fit that sequence. But as we already saw, there's a problem there. Remember I was talking about cake cutting the other day? My pattern went, 1 cut gives you 2 pieces, 2 cuts gives you 4 pieces, 3 cuts gives you 8, 4 cuts gives you 16, but 5 cuts only gives you 31. You have to have a large enough part of the pattern to be able to find it uniquely in here. And sometimes I get an answer out of here that doesn't help me very much. I believe it's number 15 in this section's exercises. No, it's example 15. right under this list. The list goes 1, 3, 4, 7, 11, 18, 29, 47, say. This is kind of like the Fibonacci sequence, but it didn't start with 1 and 1. It started with 1 and 3. Francois Lucas developed a whole book of this idea. He said, I'm going to do this Fibonacci-like recurrence. I'm just going to start with different things and look at what comes out. So this is called a Lucas sequence. There are hundreds of these. But I will look up a sequence on this website and I'll get, this is the number, the Catalan sequence number 37. What? That doesn't help me. So even knowing that this has a name isn't always enough. I want to be able to verify and understand where the formulas that it pulls out comes from. Questions? How many of you have a bank account? Your bank account's a geometric series. Your bank account pays interest. It may pay a piss amount of interest, but it pays interest, right? So if I stick $1,000 in the bank account and I leave it there, let's assume for a moment I earn 1%. A year, a month, whatever, a time unit. Let's go with a year. How much money's in the bank account at the end of the year? I didn't touch it. I stuffed it in there. I waited a year. What do I get? Get 10 more bucks, right? The future amount is the principal plus the interest. Interest is the amount times the rate times time. $1,000 at 1%, 10 bucks added on, right? That was for 1 year. What happens at the end of year number 2? I forgot about this checking account. I don't know. I haven't looked at it. The money's just sitting there earning. What happens? Aha. I don't start with this much at the beginning of the year. I start with this much at the beginning of the year. 1 plus 0.01 times 1. 102,010. Notice that this expression in the parentheses is exactly the same as this expression. I've got a geometric sequence. Every year I'm going to multiply by that thing. Which means after however many years, I will have multiplied by the same number over and over and over and over. Geometric sequences are the backbone of the banking system for precisely this reason. Here's another one. This one is a little more algebraic. I want you to take a number, any number at all, plug it into that equation. Take what you get out and put it back in. So this time, instead of multiplying by the same thing over and over, you're going to apply the function a second time. You're going to apply the function a third time and a fourth time. I want to know what happens based on your number. So somebody give me a number. 8. So 8 squared is 64. 64 times 64 is 4096. This is going to get really friggin' huge really fast, isn't it? I am 100% confident that your number is going to blow up to infinity as I keep doing this feedback process. Somebody give me another number. 1. 1 squared is 1. 1 doesn't go anywhere, does it? As a matter of fact, there's only one other number that stays fixed. 0, right? But there's another number that eventually stays fixed. X equals -1. Because -1 squared is 1, and then you're stuck at 1, right? If you just keep squaring, you're never going to escape 1. Somebody give me a different number. Well, 2 is going to blow up as well, right? Because 2 goes to 4, 16, 256, that boom. Turns out the number line is divided into exactly 2 pieces. If you pick a number bigger than 1 or smaller than -1, eventually it blows up to infinity. If you pick 1, you stay right there. If you pick 0, you stay right there. We have yet to pick a number between -1 and 1. What if I pick a half? As a matter of fact, every number between -1 and 0 goes to 0. So does every number between 0 and -1. The entire line can be divided into 2 pieces, the part that blows up and the part that doesn't. If I change this from using real numbers to using complex numbers, then I get a circle. Everything inside the circle squishes down to 0. Everything outside the circle blows up. If instead of using x squared, I use x squared plus something, this shape changes radically. Here's the fun part. If I pick a big number, like x squared plus 1/4, nothing stays. Everything blows up. Fractals. I give you a Julia set and its companion, the Mandelbrot set. My PhD research was about this idea. Only I didn't use squares. I used x to the 2.5. That's up, isn't it? There's something weird going on there, and that was why it was worth it. I have more to do in this chapter. That is why we will continue this on Wednesday. I will see you all then. If you came in late, come give